Geometry Common Core, the June 2016 Regents exam, starting on the last part 3, question number 34. In the diagram below, triangle A prime, B prime, C prime is the image of triangle ABC after a transformation. Describe the transformation that was performed and explain why the triangles are similar. So there were a lot of people when this question was given on Regents, I remember, that just said dilation. And that's true. We know that there are 4 types of transformations. There's rotations, reflections, and translations. Those are the rigid motions that don't change the size. A dilation is the one transformation that does. And it's pretty clear here that this is a different size. So it's definitely a dilation, but that didn't give you any credit because it says describe the transformation. When it comes to rotations, you need to say from where, how much. Reflections, across what line. A translation, by what vector. A dilation is like a rotation in that you need to say from where and how much. So where is this being dilated from? One of the ways to figure that out is to draw the dilation lines, I call them. I don't know if that's actually the technical term. So if you connect like corresponding points, like let me try to be accurate here, like B to B prime, and trace it back, and the same thing with A to A prime and trace it back, and C to C prime. Sorry, you'll notice that they're all crossing at the origin, and so that must be the center of dilation here. So this is a dilation from the origin. But then we need to figure out what is the scale factor, or the ratio. And it certainly looks like it's greater than 1 because it got bigger. I mean, here is AB, here's the original, and then it got this big. But exactly how much bigger is it? Can we assume it's a scale factor of 2 or something like that? No. Let me actually clear out. I'll keep those. So we need to figure out what that scale factor is. Well, we could count boxes. Like if I use BC as an example, it's 1, 2, 3, 4, 5, 6, the length of 6. And B prime to C prime is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's where it would be if we're a scale factor of 2. But it's 13, 14, 15. 6 to 15. What is the scale factor that brings 6 to 15? It's certainly not going to be a nice, simple scale factor, but one of the things you always should remember about the ratio for a dilation scale factor is the ratio, you always want to think of it as, new over old. The scale factor is always new over old. So if you have a new length like 15, put it over an old length like 6. And if you do 15 divided by 6, I think that comes out to be 2.5. Pretty sure. Let me double check that on my calculator here. 15 over 6 is 2.5. Turn that on. 15 over 6 is 2.5. Right. So that's your scale factor. It's a little over 2 times because it's not going from 6 to 12. It's 2.5. So what we should really say here is a dilation about, or you could say, or centered from, or centered at, a dilation about the origin, or you could say a dilation centered at 0, 0, or centered at the origin, with a scale factor of 2.5, or you could say by ratio 2.5. That's how you successfully describe the transformation. Now explain why they are similar. Well, basically explain what a dilation does. A dilation changes side lengths proportionately but preserves angle measure. So I'll say since all corresponding angles are congruent, therefore the triangles are similar. Certainly not the only way you could phrase that. You could mention how a dilation produces parallel lines and corresponding, something like that. But that would certainly be enough right there. So dilation about the origin with a scale factor of 2.5. And a dilation changes the side lengths proportionally but preserves angle measure. And that's what similarity is. Sides are proportionate, angles congruent. But since all corresponding angles are congruent, the triangles are similar. All right, so that's it for the part 3s. Let's look at the first part 4 here. How about this? Let me go to the next page. Sorry, having technical difficulties. Pause for 1 second. Sorry about that. All fixed, at least I hope. So, number 35, the first part 4 of this exam. Quadrilateral ABCD with diagonals AC and BD bisect each other, and angle 1 is congruent to angle 2. So the diagonals bisect each other. So that means that this diagonal is bisected and this diagonal is bisected. And they're also telling us angle 1 is congruent to angle 2. Prove 2 things here. Triangle ACD, so this triangle here, prove it's an isosceles triangle. Well, that would only be true if it had 2 congruent sides, meaning these sides were congruent. And that would only be true if this whole shape were a rhombus. And prove triangle AEB here is a right triangle. That would only be true if these diagonals are perpendicular, which would only be true if this were a rhombus. See, this is, a nice proof, honestly. It's a good question, but it's very hidden. It's basically, it's a backwards way of kind of asking you to prove that this thing is a rhombus. And, by saying, make this a right triangle, which means this is perpendicular. Prove this triangle is isosceles, which means adjacent sides are congruent. Again, these are rhombus concepts. So you have to kind of be able to read between the lines in these part 4 proofs. When they're asking you to prove this, or when they give you this, what are they really saying, or what do they really want you to prove here? And, the big part of what's given to you and what they're trying to say, that's a big part of it. Like diagonals bisect each other. That has to, kind of have a red flag in your mind that, diagonals bisect each other. Where have I heard that before? Oh, that's a property of a parallelogram. In fact, that's a way to prove a parallelogram. So by telling me the diagonals bisect each other, that's their way of telling me it's a parallelogram. And then why are they telling me angle 1 is congruent to angle 2? Well, that means that this diagonal is bisecting this angle. And if it's a parallelogram with diagonals that bisect angles, that's the problem's way of telling me it's a rhombus. And if it's a rhombus, then I have congruent sides and perpendicular diagonals. And so, like, this problem, it would have been much easier if it just flat out said, you're given it's a rhombus, prove it's an isosceles triangle, and prove it's, but that's essentially what they're doing. They're just kind of saying it in cryptic ways. And that's the challenge of these proofs. So let's hear. I want to do this on a separate page so I can look on and see what's happening. So statement, reason, proof. First thing, AC and BD bisect each other. That's given. And what this proves is parallelogram ABCD, because it's a quadrilateral with diagonals that bisect each other. Sorry, occasionally when I'm writing, it throws that black line in there. I apologize. And so remember, there's 4 ways to prove a parallelogram. Both pairs of opposite sides parallel. Both pairs of opposite sides congruent. A single pair of opposite sides is parallel and congruent, or diagonals bisect each other. And that's what they tell you. So if they tell you a quadrilateral diagonals bisect each other, they're telling you it's a parallelogram, and you have to recognize that. Then the fact that you're given angle 1 is congruent to angle 2, that's enough to prove rhombus ABCD, because now it's a parallelogram with diagonal angle bisectors. And there's a couple ways to prove a rhombus. A rhombus, if you could prove adjacent sides are congruent, or if you can prove diagonals are perpendicular, or if you could prove a diagonal is bisecting an angle. And that's what they gave us, is they gave us a diagonal bisecting angle. So they gave us a parallelogram, they gave us a rhombus, they just gave it to us in a hidden way. And then as a consequence of this being a rhombus, we can say AD, oops, sorry about that, I don't know why that's still writing. Try that again. AD is congruent to DC because all sides of a rhombus are congruent. And we could say that from there you could say triangle ACD is isosceles because a triangle with two congruent sides. So that part's done. And then we could say that AC is perpendicular to BD because the diagonals of a rhombus are perpendicular. And then we could finally say triangle AEB is right because it's a triangle with perpendicular sides. I mean, you could go into more detail and say perpendicular lines form right angles and a right triangle has a right angle and all those things, but I think this is enough. So by saying all this, by saying, you know, given that the diagonals bisect each other gives us it's a parallelogram. Given that it's a parallelogram with a diagonal angle bisector gives us a rhombus. And because it's a rhombus, adjacent sides are congruent, which means that this triangle is isosceles because it's got two congruent sides. And given that it's a rhombus, kind of given that it was a rhombus, we know the diagonals are perpendicular. And if the diagonals are perpendicular, that means this triangle is a right triangle. So it was all about seeing and understanding what they gave you was enough to prove a rhombus, and a rhombus is easily then able to prove all this other stuff. Okay, so that's the first part 4 of this Regents. The next and last video in this sequence, we will discuss the last part 4, the volume part 436. Like I said, I think in the last video that there are no more volume part 4 questions, at least that's what we've been told on the Regents, but I'm still going to go over this question because it's a nice question to go over, and that'll wrap up our June 2016 exam. See ya.